Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brains. Like many of you, we were pleased to wake up to the news that the second Crew Dragon had launched humans to the International Space Station. Sharing its name with Space Shuttle Endeavour, this capsule, with its crew of 3, took off without a hitch and will be discussed in next week's Rocket Roundup.
While Dragon celebrates its second crewed launch, Hubble is up there celebrating its 31st birthday. Launch of the Hubble was delayed to 1990 after the loss of the Space Shuttle Challenger. But there's no denying this millennial glasses-wearing style. As a reminder, that is a great telescope still doing great science. NASA and ESA released this stunning image of the massive star AG Carinae. With 70 times the mass of the sun, this luminous blue variable periodically undergoes violent outbursts, during which it expels mass. In Hubble's image, the star can be seen glowing brightly in the center of a ring of glowing material. This nebula is about 5 light years across and is made of 10 solar masses of material that AG Carinae has already blasted to space. For perspective, the Sun and the Alpha Centauri systems could fit nicely within this bright halo.
And speaking of the Alpha Centauri system, its smallest member, the red dwarf Proxima Centauri, has been spotted giving off a massive stellar flare, the likes of which we are alive to say the Sun hasn't been observed to produce. In fact, this single flare was 100 times more powerful than similar events produced by the Sun. It's long been known that tiny red dwarf stars can have powerful flares. And this activity is part of why it's hard to know if planets around red dwarfs can support life for prolonged and continuous periods of time. While reviewing archival data of Proxima Centauri in the Atacama Large Millimeter Array Archive, researchers discovered that this nearest star to the Earth had a flare in 2018. In hopes of catching a second flare, the research team sought and was awarded 40 nights of observing time spread over many months on 9 telescopes on and above the Earth. During this period, one 7-second flare was observed. During this event, the star became 14,000 times brighter in many different colors of light, including both ultraviolet and radio. Lead author of this work, Meredith McGregor, points out Proxima Centauri's planets are getting hit by something like this not once in a century, but at least once a day, if not several times a day. If there was life on the planet nearest to Proxima Centauri, it would have to look very different than anything on Earth. A human being on this planet would have a bad time. These results are published in the Astrophysical Journal Letters and have implications for everyone from stellar astronomers to astrobiologists. They also make me wish that the energy of solar flares was brighter in visible light. Imagine looking up and seeing a star get 10,000 times brighter for just a couple of seconds. If we could see in radio or ultraviolet, we'd see that. It also might be a bit traumatizing. Like a sky was filled with lights on the fritz. So maybe it's for the best that we don't actually see that.
From giant flares, we now turn to giant planets. Now, I love when we directly image exoplanets. It's an amazing accomplishment and truly shows how we continue to push the limits of our technology. And sometimes those images reveal planets that make very little sense. Such is the case with YSES 2b, a giant planet about 360 light years away and orbiting at a distance 110 times farther out from its star than the Earth is from the Sun. That's also about 20 times farther than Jupiter orbits. And when we say giant, we mean it's 6 times heavier than Jupiter. So what, Beth? Maybe the star is huge. Nope. The star resembles our own sun, but much younger, only 14 million years old. All of these numbers led a team of astronomers to try and understand just how and where this planet formed. Large planets need a lot of material, and we don't find that much in the accretion disks of protoplanetary systems at that kind of distance. It's also not heavy enough to have been formed from a gravitational instability in the protoplanetary disk, which means it's possible that it formed close in and somehow migrated out. But that requires the influence of another planet, and that planet has yet to be found. The team is going to continue to look for that sibling planet as well as other gaseous planets around young sun-like stars. We'll bring you their findings here on the Daily Space. Up next, we're going to talk about meteorites, carbon dioxide, and Mars. Trust me, folks, these all go together. Stay tuned. The chemistry of meteorites and planets allows us to link together and understand more of our solar system's history and help us maybe survive exploring that solar system. One of the biggest mysteries of our solar system's formation is how Earth ended up with so much water. There is a hypothesis that some, if not all of the water, came from asteroids that hit the Earth during a period known as the Late Heavy Bombardment. You see, those asteroids formed out beyond the ice line, meaning that instead of dealing with gaseous or liquid forms of H2O and carbon dioxide, these bodies were infused with frozen forms. And when a bunch of them collided with the young-ish Earth, all that ice was heated up and released in liquid form or possibly gaseous form and held onto by Earth's gravity. That's good for us since we require said water to live. And now an analysis of the Sutter's Mill meteorite has provided a bit more evidence for the water and carbon dioxide came here from afar hypothesis. The meteorite fell to Earth back in 2012, and due to witness accounts of the fireball and radar data, several pieces were found by my SETI Institute mentor, Peter Yenniskins. Now, a team has analyzed some of the tiniest inclusions in the minerals of the meteorite, frozen bits that were trapped inside and are now liquid but still trapped. And they found carbon dioxide-rich water. Per the press release, this would require the asteroid to have formed in a part of the solar system cold enough for water and carbon dioxide to freeze, and these conditions would place the site of formation far outside of Earth's orbit, likely beyond the orbit of Jupiter. The asteroid must then have been transported to the inner regions of the solar system where fragments could later collide with the planet Earth. But they didn't just collide with Earth. Mars, too, has water and carbon dioxide, but frankly, more of the latter is what makes up the atmosphere. Again, the only habitable planet for humans is Earth. Mars will kill us without a whole lot of precautions, and we're still trying to figure out what resources we need to bring and what we can pull in situ, or from the red planet itself. To that end, an instrument on the Perseverance rover called MOXIE, or Mars Oxygen In-Situ Resource Utilization Experiment, successfully accomplished what could turn out to be a major first. It converted carbon dioxide in the atmosphere into oxygen. This is another technology demonstration, like the Ingenuity helicopter, that could turn into something more with further development. However, the question was, is further development worth it? NASA likes to experiment, sure, but they really like things that work before they go into space. And it seems MOXIE works. As the article states, while the technology demonstration is just getting started, it could pave the way for science fiction to become science fact, isolating and storing oxygen on Mars to help power rockets that could lift astronauts off the planet's surface. Such devices also might one day provide breathable air for the astronauts themselves. The atmosphere of Mars is 96% carbon dioxide. Again, not good for humans. So MOXIE separates the oxygen atoms out of the carbon dioxide molecules using a high heat process, 800 degrees Celsius. Well, it grabs one oxygen atom. The other one stays with the carbon and is released as carbon monoxide into the atmosphere. Still not good for humans, but hey, now we have oxygen we can use to breathe and to make rocket fuel to get back to Earth. It's a start anyway. One final meteorite story for you. Earlier this year, we reported that Bennu appears to have pieces of Vesta mixed in with its rocks, and now it turns out that a meteorite we reported on a couple years ago may also be from Vesta. Back in 2018, fireball was seen streaking across African skies and was traced to an impact area in the central Kalahari Game Reserve in Botswana. Again, Dr. Yanniskins of the SETI Institute used radar data and witness accounts, as well as help from the local scientific community, to locate fragments of that fireball. 23 meteorites were recovered from the event, pieces that survived the destruction of a 1.5 meter parent object. Analysis of these fragments, as well as pre-impact images taken by the Catalina Sky Survey and the Sky Mapper Southern Survey, allow us to understand the meteorite better than any other object so far recovered. From its chemistry, it appears, these pieces are actually pieces of Vesta that got knocked off billions of years ago during an impact, and through a confluence of orbits, were able to hit our world in 2018. It's a rock universe out there, which for us means free samples of space rock, no robotic sample missions required. After the break, we'll be back to talk about how much our human desire for symmetry keeps mucking with our ability to understand physics.
In a new article in Science News, correspondent Tom Siegfried articulated a problem that has come up in bits and pieces in this show in recent weeks. This problem, put as simple as possible, is we don't understand why the universe has the particles it has. And this is making it really hard to figure out what undiscovered particles are out there waiting to be found as the bits of stuff behind dark matter and maybe even dark energy. In trying to guess at what might be out there, physicists have, as they always have, relied on ideas of symmetry. This sometimes works. Symmetry allows us to figure out the three families of particles that make up the detectable universe, from the foundational quarks up through to the protons, neutrons, and other particles that quarks can build. Symmetry, however, does not always help. Early researchers trying to understand the motions of the planets relied on the ideas of perfect symmetry in Plato's solids. From Ptolemy and Copernicus down through Kepler's early work, planets were assumed to orbit in perfect circles, and since perfect circles' orbits don't match what we see, planets going in circles attached to circles and other crazy combinations of perfect shapes were utilized to try and force symmetry into celestial motions. It didn't work. And it was only in considering the imperfect ellipse, which is only symmetrical if cut in half just right. Well, it was in considering the ellipse that Kepler solved planetary motion by throwing away complete symmetry. And now we know that while some orbits are circles, a special kind of ellipse, all orbits are ellipses. With particle physics, we know that there is symmetry in what we see today. We know that there are things missing from our model. In trying to find what's missing, researchers such as Nobel Prize winner Steven Weinberg have created new families of supersymmetric particles that they can mathematically describe, but that no one has been able to find. This is the theory of supersymmetry and its myriad of supersymmetric particles that are paired to the particles we already have found, but we can't find them. While this theory hints at underlying math that explains their characteristics, the theories lack underlying physics. Newton eventually found gravity to explain orbits, but no one has found that thing that makes the standard model work or leads us to other particles. And with each new set of observations, we are eliminating more and more predicted possible particles and not really finding any. Over the next 2 years, the combined efforts of the Large Hadron Collider and Fermi National Lab and all the neutrino and gamma ray detectors around the world are going to rule out supersymmetry or finally find something. It's going to be one or the other. but we've already ruled out a lot. And it seems like it is time for us to start saying, let's break the concepts of symmetry and look at things from a less perfect angle. As any artist knows, it is not in perfectly centering and perfectly mirroring scenes that beauty is found. The golden ratio and all its mathematical siblings bring beauty to everything from photography to flower petals to the shape of spiral galaxies. Beauty comes in the asymmetry, and perhaps even at the most fundamental level, at the level of particle physics. It's now time to look for asymmetry as the answer. After the break, we'll be back to take a look at Google Earth's new time-lapse feature. Stay tuned. Earlier this week, we mentioned a new feature brought to Google Earth that allows you to now explore tens of thousands of images added from historical satellite datasets. In the promotional graphics and videos that came with that announcement, we saw amazing pictures of what things looked like in 1984 and what they look like today in 2020. In the selected images that were used for this promo, I got the impression that I could go in and look in detail at the farms around where I live now and at the cities I grew up in. And I said we'd provide a review of this software, and this is our Friday afternoon review segment. And Google Earth, you're under review. So, as someone who lives in my browser most of the time, I started by going to Google Earth in the browser. And while you can explore their pre-selected time lapses in your browser, if you actually want to explore anywhere you want, you're going to need to download Google Pro. This is a Google Pro feature, and it's fine. It's easy, it's free, it works on pretty much any operating system. But once you get it downloaded, what you may find, as I found, is the biggest change from 1984 to 2020 is one of resolution. This was the most zoomed in I could get in on the city of Boston in the 1984 image. If I tried to zoom any more, 1984 is on the right, 2020 is on the left. If I tried to zoom in any more, it just blurred out and basically said, hey, I don't have images for you here. So this allowed me to basically see that the color corrections changed from 1984 to 2020. This was not as satisfying as one might think. From my hometown of Boston, Mass., I jumped to where I live today in Edwardsville, Illinois. This is a small town that I know is greatly growing as our university expands and, well, as is happening in so many places, Amazon is building warehouses. In the top image in 2020, you see, well, all those warehouses of today. And you see a lot of, well, more farmland than there was in the lower image from 1984. Or I guess greener land? It's hard to tell because, again, the biggest change between 1984 and 2020 was one of resolution. If you're trying to monitor the extent of cities that are growing and building more and more suburbs, it's going to help. If you're trying to find all those giant warehouses being built, it's going to help. If you want to explore your own backyard, you're out of luck. It's a start. It has a way to go. But for now, this has been today's Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.